Yeah, good morning, everyone. So we'll go over lab uh, material, say today or maybe uh, early Wednesday, and then we'll go back to the frequency response of BJT. Okay. So yeah, the first one is I think today you will do the lab number 9, right? Frequency response of BJT circuit. Next week you'll do MOSFET SPICE parameter extraction and MOSFET amplifier and MOSFET switch circuit. Okay, and then you'll go to lab 11, which is MOS differential amplifier. Then ECG and PCG amplifier. That's it. Okay. So let's go review MOSFET IV characteristic. Okay. Yeah, we looked at the BJT. BJT is a bipolar junction transistor. So BJT consists of two PN junctions very close together. Okay. So MOSFET, we just review IV characteristic. Yeah, MOSFET is just metal oxide semiconductor field effect transistor. So metal oxide semiconductor represents the structure of MOSFET. MOSFET structure is just a metal oxide and then semiconductor. Say you have so this metal is connected to gate, and then those N plus junctions are connected either to source or drain. Yeah, this P is a substrate bulk, or sometimes we call substrate. Yeah, this is an N-channel MOSFET. Yeah, the this N-channel stands for free electrons contribute to current flow. So when gate voltage is positive, you know, when gate source voltage is positive and larger than threshold voltage, this source, which is N-type, supplies sources those electrons. This drains this P channel. I mean this electron, right? So this source is free electron. Those are free electrons, right? So current flows from drain to source. Electron flows from source to drain. This yeah, this is a P-type. So those drain bulk junction and source bulk junction must be always reverse biased, right? Those must be reverse biased. It is a four-terminal device, right? Four-terminal device. Because I have a gate, drain, source bulk contact. Okay, those are 4 terminals. Yeah, electric field on this vertical electric field, controls the current flow. Vertical electric field controls the amount of free electron in a channel and controls the amount of current flow. That's why I have a field effect. Field effect. The field represents the electric field. This field effect vertical electric field controls the amount of current flow. Okay. So this is just a review, right? So gate source voltage is smaller than, smaller than threshold voltage. This threshold voltage may be around 1 volt. Then my drain current is 0. This is a cutoff. If gate source voltage is larger than threshold voltage and drain source voltage is smaller than VGS minus VTH, this is called triode region. This triode represents the vacuum tube. When gate source voltage is larger than threshold voltage and drain source voltage is larger than VGS minus VTH, this is called the saturation region. Saturation. So this saturation is you eat a lot and you are happy. So the current voltage characteristic looks like say when VGS equal, for example, this is 5 volt. Okay, when VGS equal 4 volt, so yeah, when VGS equal 3 volt, so this is the boundary between triode and saturation. This saturation means current is saturated. Current is saturated. Current is saturated because current doesn't increase much. BJT saturation is voltage is saturated to 0.2 volt. Okay. They have a very strange terminology. Yeah, we will use saturation region for amplifier. Okay. Yeah, for amplification, see, at a given drain voltage, see, this represents GM times delta VGS. Say here triode region, GM times delta VGS is smaller than saturation region. So transconductance GM is largest in the saturation region. That's why we use saturation region for amplification. Question? 인풋이지. 그러니까 서킷 로테이션을 하면은 보통은 인풋이지, 인풋. 그래서 요게 요 델타 ID가 같은 드레인 소스 전압에서는 이렇게 표시된다는 거죠. 그러니까 예를 들어서 델타 ID는 그 얘들이 다 어떤 인풋하고 관계 있는 거죠. 예? 델타 VGS 같은 것들이. 그렇지. 지금은 GM 얘기를 했고 나중에는 GMB 델타 ID를 VBS로 미분하면은 GMB가 되는 거죠. 그래서 여기서 이 텀이 도미넌트 하죠. 도미넌트. 네. 벌크 항상 연결돼 있어야 돼요. 표시를 안 해서 그렇지. The most negative potential에 the most negative potential에 붙여놔야 돼. 항상. 얘는 어디 붙든지 상관없이 얘는 어떤 DC에 붙어, DC. The most negative potential. 그래야 소스 드레인 장션이 항상 리버스 바이어스가 걸려 있거든요. Okay. So circuit notation is N-channel MOSFET, P-channel MOSFET. Say I can represent it like that. Yeah, this is N-channel MOSFET. Say so in N-channel MOSFET, VD is always larger than, because the electron flows for current conduction. This source must be negative, more negative than drain to push electrons from source to drain. Yeah, P-channel MOSFET. Okay, come back quickly. Okay, so see this arrow represents the position of a source node, and also the flow, the direction of current flow. Okay, see it says the current flows from drain to source. This PMOS says in the PMOS free electron flows for current conduction. So source voltage is more positive than drain voltage to push free hole to the drain. Okay. Okay, let's go back to the, start the circuit. See, see, if I put, this is MOS, I am skipping the bulk node. See, if I put like that, and then this voltage is some V, drain and gate are connected together. Yeah, my threshold voltage is positive. Yeah, it's called enhancement MOSFET. enhancement MOSFET is it is off. So at the VGS equals 0, current doesn't flow. So I have to enhance the gate source voltage for current conduction. So in the NMOS, I have to enhance in a positive direction. Threshold voltage is positive. For the P-channel enhancement MOSFET, my threshold voltage is negative. I have to enhance in a negative direction for whole flow. Okay. So here see my drain source voltage is the same as gate source voltage. Yeah, that's V. So this one, see, when V is larger than threshold voltage, yeah, see, this works in a saturation, okay, saturation region. This works in a saturation. So my current I, gate current is 0, because it's an insulator. My current I will be when V is less than threshold voltage. So the IV characteristic of this one, so until threshold voltage, it is 0, current is 0, and then it follows that square law relation. Okay. So yeah, this circuit, see, this inverting amplifier, yeah, if there is a current flow I, yeah, this VI should be, this is 0, minus I times 1.2K, okay? Because see, this voltage drop is 1.2K times I, right? So it is negative, yeah, from here to ground. There is a virtual ground because of negative feedback. So yeah, this voltage is 0. Then I will apply current using some function generator or maybe some DC voltage source. Yeah, I have this one, this bulk. You can see this is NMOS, right? See, in a bulk, it's just something like that. Look at this arrow. This arrow represents, see, bulk is P-type, PN. Those are source drain. So it says if bulk is forward biased, current will flow that way. So so this arrow represents I have a P-type substrate, P-type bulk. For the P-type bulk, yeah, it's a N-channel MOSFET. So yeah, see, this should be the most negative potential in the circuit, which is 0, right? I think this MOSFET you can bias. I'm not sure exactly 3 volt minus 3 volt. Those are DC bias for those MOSFET. And so this VBB can be 0 volt. That's the most negative potential of this MOSFET circuit. You change this V value and monitor I current here. Okay. Then you can see if you put square root ID in a Excel, 아? 아, COX는 게이트 옥사이드 캐패시턴스. 그 MOSFET 게이트 옥사이드 thickness. Okay. So if you, however, if you plot those square root ID versus VGS, say we expect something like that. However, you will see something like that. Okay, actually something like that in real measurement. So you need the operating region with the highest slope to find the threshold voltage. Okay, this mobility is reduced as gate voltage is increased. Okay, question? No? No, actually, I forgot mention one thing. Let's see. It is, yeah, triode. Triode gate source voltage is larger than threshold voltage. Gate drain voltage is larger than threshold voltage. Yeah, in this case, my ID will be yeah, in a saturation region. So, you can write this one VGS equal VGD equal VGS minus VDS. So my VDS is less than VGS minus VTH. Yeah, they're same condition. Okay. Yeah, this ID we have some sort of early effect. We call this one channel length modulation. Yeah, we'll use those one. For amplifier will operate MOSFET in a saturation region. Okay. Okay. Question? No. Uh, uh, uh. 그거는 영향을 안 주는데요. 여기 보면은, 그러니까, 근데 이 VDS가 VDS도 약간 그거 하네. 그러니까 지금 EV나 같잖아요. 그죠? 얘는 도로 올라가는 영향을, 약간은 올라가는 거죠. 별 차이 안 나지만 약간 올라가는 영향을 주는 거고, 이 모빌리티가 게이트 전압이 증가하면 감소하게 돼요. 모빌리티가 감소. 그래서 이렇게 누워버려요. 여기 직렬 저항이 달려 있더라도 무슨 그런 눕는 효과는 있어요. 근데 주로 모빌리티가 감소해요. Okay, next one. Mobility and lambda. how can I calculate the mobility lambda? Again, by virtual ground, this is 0 volt. Yeah, this Vy is just ID minus ID times 1.2K. Okay. Then see, so this source is 0, bulk is 0. Then I need some positive supply and also negative supply for this op-amp. Yeah, I have some protection register. Say, yeah, actually, if you plot function generator, you can watch a Lissajous pattern here. Yeah, this is Vx and Vy. Yeah, this Lissajous pattern will look like this VDS from function generator, this Vy from this output node. Yeah, the Lissajous pattern will look like that. Constant VGS curve, right? Constant VGS curve. See, my gate source voltage is fixed at the 3 volt or 4 volt. Threshold voltage is maybe less than 2 volt, okay? So from here, you can expect mobility. See, let's just see. Yeah, if I plot, so this is constant VGS equal, for example, 3 volt, okay? Constant. So this is VGS minus VTH. Yeah, yeah, from around here, so, you know, this current will be half mu Cox W over L VGS minus VTH square. Oh, actually, sorry. If you have something like that, yeah, this one is say something like extrapolation of this saturation region characteristic. Okay, at the VDS equals 0. You know threshold voltage. If Cox and W over L is given, you can calculate the mobility. Okay. Yeah, this is slope. Yeah, so you measure, don't use a function generator to measure current. You just change supply voltage one by one and then measure all those currents, okay? All those current. Yeah, you can use your diskette, 3.5-inch diskette, or so you monitor those current. Then by using some linear regression, by using those curves, you can find this abscissor, or you can find the slope. So what's the slope? Yeah, so yeah, your current equation. So this value is that value. Then so you can find this slope, right? This slope is let us see the ratio. Yeah, this slope is from that slope you can find this lambda. Okay. Yeah, for example, if this lambda is this is a 5 VDS equal 5 volt, and then at this 0, yeah, see by the ratio, yeah, this is actually ID2. This is ID0. This is, for example, this is ID5, ID0. Then what's lambda? Yeah, ID5 divided by ID0 should be 1 plus lambda 5 volt, right? Then I can find the lambda, okay? Question? No? Alright, so yeah, now we go to the amplifier. Yeah, for the amplifier, I have to operate this MOSFET in the saturation region. Say, yeah, again, see, I have this negative feedback circuit. Then I have a virtual ground here. So this is 0 volt again. So this Vy will be again minus ID times 2.2K. No, this time 2.2K. So that's ID. Then, so I have some DC voltage here. Do I have a function generator? No. Okay. How can I calculate the gain? So here, see, yeah, my circuit look like that. This is N-channel MOSFET, 5 volt, and then 1.2K here. Yeah, this is my VO. This is my VI. So I can assume this is ground. So this is ID. So I'll have some gate voltage. So I need some DC gate voltage here. See, maybe, I'm not sure exactly. Say you can put something like a 3 volt plus very small sine wave here. Say this sine wave may be very small, very low frequency. Okay. Then this 3 volt and 1.2K must put this NMOS in a saturation region. Say, you know, yeah, let's put those two eyes here, and this is my VO. What's I and that VO characteristic? From transistor characteristic is a constant VGS curve, and then this 1.2K, that load line, you can put load line like that. So this one is 5 divided by 1.2K, which is around 4 milliamp, right? So that's my load line, okay? Load line. So that load line must cross this MOS characteristic in the saturation region, which is, this is a VGS equals 3 volt, for example. This is 3 volt minus threshold voltage, right? If I put large resistor, two large resistor, for example, 5K, then I have a large voltage drop there, right? So this voltage will be reduced. That can be seen in the load line like that. So in this load line, this voltage is 1.25K, which is only 1 milliamp. So then the transistor works in a triode region. Yeah, GM is small in a triode region. Okay. So I have to control resistance value and gate source voltage to operate the transistor in the saturation region to get large voltage gain. Okay. Yeah, this one is actually sees large signal characteristic, I think. Okay. I think large signal characteristic. See, I can change this voltage sweep this voltage. See, for example, yeah, I can sweep. See, when this input voltage, gate source voltage is smaller than threshold voltage, the current characteristic looks like that. My operating point is here. So if I increase gate source voltage a little bit, yeah, my VO is there, right? My VO is reduced a little bit. Say, if I increase VGS too much, yeah, my VO will be further reduced, right? So if I plot VGS, which is input voltage, and the VO, yeah, when VO is very small, it just stays at the 5 volt, and then reduces a little bit, so it goes asymptotically to 0, okay? How about those current characteristic, ID? Yeah, current is initially 0, right? Current is initially 0. You know, this current is 0. Current increases a little bit. Current increases a lot, right? Something like that. Current will keep on increasing because, you know, current will keep on increasing, right? As VGS is increased. So high gain region is here. This one. Yeah, in this one, this MOSFET in saturation region. Actually, MOSFET is saturation region, although all this region. MOSFET is a triode region here. You can see MOSFET is a triode region for high VGS. Question? 그냥 가정 1.2K인데 원래는 1.2K는 우리가 원하는 데 딱 가 있어서 만약 5K로 증가시키면 볼티지 드랍이 5K에 더 나타나가지고 VO가 줄어들 것 같잖아. 근데 그걸 보인 거예요. 여기 5K로 하면 과연 줄어들어가지고 VO가 줄어들어 버렸죠. 여기서. 그죠? 네. Okay. So next time, if I increase this number of transistors into 2, what happens? See, see, I have a parallel connection of those two, like that. So my current driving capability increased twice, right? So here, see, for the same VGS 3 volt, my current will be increased twice, right? Twice, okay. Oh, is it twice? Okay, it will go to triode, so I have to move. So here, see, if I put 2 current here, you know, my VO will drop more sharply because of large voltage drop across this 1.2K resistor. Yeah, current will be increased again, right? Twice. So I have a higher gain. You know, that slope determines my voltage gain. Okay, voltage gain. Voltage gain. This is gain, right? My voltage gain. 다 게이트하고 드레인을 같이 병렬하는 거죠. 소스도 그렇고, 벌크도 그렇고. So if I increase the transistor into 2, my GM will increase twice. And then, here see my voltage gain. This voltage gain will be, okay. So if I increase the transistor into 2, my GM becomes twice. Voltage gain will be almost twice. Yeah, here, yeah, it shows the one. So what's the voltage gain here? Yeah, I adjust VGS so it works in the saturation region. Then see this VO, yeah, that VO will be has some DC component and small signal component, right? So you can see VO, yeah, ID. Yeah, this is my ID. Okay. So I have my load line. This is my load line, okay? My load line. See, when small signal voltage is 0, yeah, my transistor curve will look like that. So this is my DC operating point. This is my DCOP, okay, DCOP. So the current is just this is a DC operating point current. If my small signal voltage is just slightly positive, my gate source voltage increases a little bit. So my transistor characteristic will move like that, okay? So my operating point is here. See, my VO, small signal VO becomes slightly negative, right? Yeah, current increases a little bit. If my small signal Vi is small and negative, entire gate source voltage becomes smaller. So yeah, IV characteristic look like that for Vi negative, right? So my small signal VO becomes slightly positive, okay? So you can see, I just move this DCOP point into origin 0, 0. Yeah, see, then this is my Vi, and what's my small signal ID? Small signal ID is something like that. Is it right? Yeah, this will be slightly larger than, positive peak is larger than negative peak because of nonlinearity. And how about the VO? My VO will be larger, something like that, okay? Okay. So, yeah, I will convert this characteristic, this transistor characteristic into linear circuit, small signal equivalent circuit. That small signal equivalent circuit will look like that. here my VBS, see this is a B, this is S, my VBS is set to 0. So I don't have this term here. I have only those two terms. Question. Yeah, my small signal equivalent circuit is linear. So, you know, this ID will be symmetrical. Yeah, VO will also be symmetrical because in a small signal circuit, it is linear. Yeah, this is a small signal equivalent circuit. Small signal equivalent circuit is always linear. Okay, let's try to calculate voltage gain. This is CMOS. Where am I? Yeah. No. Do I have any empty space? Oh, yeah, here. See, my circuit, this is a my circuit, amplifier circuit, 5 volt, VO, 0 volt, and then I have some small signal and some DC. So my small signal circuit will be, this is a common source, which is similar to common emitter, common source amplifier, because my input port is a gate source, output port is a drain source. So I will convert this one so they are connected together, right? So here my VGS equal my input voltage, my VBS equals 0. So this is open circuited. So my VO should be minus GM VI times 1.2K times RO. So my RO is pretty large. So my RO is how large? This is lambda 1 over lambda ID. This is a DC current, pretty large. So this is yeah, that minus GM times 1.2K is my voltage gain, small signal voltage gain. Okay, question? No? Oh, how come this is just slow? All right. So that GM is just yeah. This is GM. GM is transconductance. Transconductance, eh? Trans. Okay. So in a saturation current equation, yeah, this partial derivative Yeah, you can see this is nothing but so for the same DC operating point current, if I increase W of L twice by connecting two transistors in parallel, then my GM is increased by square root 2, okay? If this is 2. Then my voltage gain will be increased by small signal voltage gain will be increased by square root 2, okay? At the same DC current. Yeah, question? No? Yeah, so let's go to the CMOS circuit. Where is my CMOS? Oh yeah, this is my CMOS. Oh, no, this is not CMOS yet. Yeah, this one is just enhancement load. See, that resistor is replaced by this MOS diode. Yeah, this is my MOS diode. Yeah, you know, substrate is connected to the most negative potential. This one, the most negative. So, you know, this IV characteristic flows current in one direction only, right? So it is a diode, right? So yeah, for this one, let's look at the this I versus VO. You know, this is a virtual ground 0, right? I VO. What's transistor characteristic? I mean, this is a driver. This is a load, right? So let's see. Driver characteristic looks the same. How about this load? Yeah, this current I should be half mu Cox W over L. Gate source voltage is 5 volt minus VO minus VTH square, right? If this voltage is larger than threshold voltage, okay? Then I can plot the load line. Load line is 5 minus threshold voltage. And then, say, this curve will be look like that, okay? So this is half mu Cox W over L VO equals 0. Okay, we hope this intersection occurs in the saturation region of driver transistor. Okay. Yeah, in this case, my small signal circuit. Let's see. What's a small signal equivalent circuit of MOS diode? Yeah, this is my diode, right? Yeah, what's a small signal equivalent circuit of this diode? See? Yeah, I will put that small signal equivalent circuit here, GM, yeah, VGS, yeah, which is V, and then GMB, VBS. Yeah, my B is here, the most negative potential, which is a DC. This is a source, this is a gate drain, right? So I have a non-zero VBS here, okay? Yeah, 5 volt is AC. Yeah, this is my small signal equivalent circuit. Okay. So here see, let's see. So this is my VO node, right? Then what's VGS? My VGS equal, this is AC 0. Okay, this is AC, small signal equivalent circuit, DC, 5 volt DC is AC 0. Okay, what's VBS? This bulk voltage is 0, right? AC 0. Okay, so I can replace this one into something, see, I will replace this one into current flows like that, which is GMVO. This is 0, this is VO. Similarly, this one is also replaced by GMVO, right? So the current is proportional to VO, which is the voltage drop across this dependent current source. Then I can just represent like that parallel connection of those three, which is resistance 1 over GM, 1 over GMB, RO, right? So the equivalent resistance is just a parallel connection of those transistors. Okay. Yeah, question. Now my voltage gain, which is, this is a driver transistor. So this is my transconductance of a driver transistor here. This is M1, okay? And there was load. My GM1 times this thing. This is the load, right? This is GM2, GMB2, 1 over RO1, RO2. Actually, 1 over RO1 is also there in parallel connection. So if I neglect all those things, this voltage gain is around. If I use the same transistor, voltage gain should be -1. Okay, around. Question? No? Actually, this is, I think you will go back in more detail in 2 weeks later, okay, in the MOSFET chapter. We'll skip that part very quickly. Yeah, let's go to the CMOS inverter. Yeah, for the CMOS inverter, I have both NMOS and the PMOS here. So this is a 5 volt. Yeah, I have NMOS here. I have a PMOS there. Okay. Here, see, this NMOS is also a driver. Yeah, it also works as a load for the other transistor. This PMOS also works as a driver and load. Okay. Because if I increase this Vi in a positive direction, NMOS current increases. However, PMOS current is reduced. Okay, the current changes. Okay. All right. So this is a 0. This is a VO, and this is I. And if I plot I versus VO, yeah, in a DC operating point, this is my NMOS characteristic, and this is my PMOS characteristic, and I have a DC operating point here, okay, DCOP. Yeah, if I increase Vi, my Vi is increased. So it means my small signal Vi is positive. Then my NMOS current increases. Uh, but you know, the PMOS source gate voltage is reduced, right? PMOS source gate voltage is 5 minus Vi. Vi increases, this amount is reduced. So current is reduced, right? PMOS current is reduced. So this is my new operating point, right? So here my DCOP, so my small signal VO becomes negative, right? As Vi changes, PMOS current and NMOS current both change. So they are both drivers. Okay. All right. So yeah, small signal equivalent circuit looks like that. You know, here, yeah, that VBS is always zero for those NMOS and PMOS. Okay. So this is NMOS VI. You can see PMOS characteristic looks like that. Yeah, so this is my GMP VI, okay? So, yeah, they are the same node, okay? So my VO should be GMN GMP times VI. This is current times, so my voltage is pretty large. Okay. Yeah, this is I increased PMOS MOS part twice. So before that, see what's large signal characteristic? Okay, large signal characteristic VI VO and this I times this I times VI. Okay. So if I change VI from 0 to 5 volt here, yeah, when you can watch this one in here, okay. So this is NMOS threshold voltage, which may be around 1.5 or something. This is 5 minus PMOS threshold voltage. PMOS threshold voltage is negative, right? Maybe minus 1.5, something like that. Yeah, in this region, NMOS transistor is turned off. You can follow like that. So here's the current characteristic. You can watch similar thing. So this is a very high gain region, both NMOS and PMOS in saturation. Okay. Yeah, the voltage gain here is just NMOS plus PMOS times RON parallel ROP. Okay. So this is pretty large, very large compared to NMOS. Okay. Yeah, if you put two transistors here, you know, NMOS becomes smaller. So for the small VI, yeah, it matches PMOS. So let's see. Yeah, this is a 2x NMOS. It shifts toward the left. Yeah, similarly, this one shifts toward the left. Okay. Yeah, logic threshold voltage is defined. See, the cross section of cross section of this curve with VO equal VI. Okay, so they work in the saturation region for logic threshold. So this voltage is called logic threshold voltage. Logic threshold. So if I increase NMOS twice, this logic threshold voltage is reduced. Okay. Yeah, the logic threshold voltage is reduced from here to there. If I increase NMOS strength by twice. Okay, question. No, I think I covered this part. Oh, switch is there. How come? Switch. Okay. Yeah, let's stop here.